Urine concentration. Urine is concentrated in the loop of Henle. Let's see how it is done. The osmolality of the body fluid, it is 300 milliosmoles per kg, and it is important to be maintained in this range. Osmolality is equal to the number of solute particles in 1 kg of water. 1 osmol is equal to 1 mole of particle per kg of water. Body fluids have much smaller amounts, so they are expressed in milliosmoles. So the osmolality of the body fluid is 300 milliosmol. Our kidneys, they produce only small amount of urine if the body is dehydrated. So that small amount of urine means that they reabsorb the water, and now the urine is very concentrated. So they produce small amount of concentrated urine if the body is dehydrated, because they are trying to preserve the water. But if the body is overhydrated, then they produce dilute urine so that water can be removed, and this is accomplished by using counter current mechanism. What is counter current mechanism? It is that the fluid, it flows in opposite direction in two adjacent segments, which with hairpin turn. So this is the hairpin turn. I just put it here so you can imagine. Just imagine this is the descending limb of the loop of Henle, and then it turns here, and this is the ascending limb of loop of Henle. Now let me just draw it here. So this is the loop of Henle. In the descending limb, the filtrate is flowing down, and then it turns around. It turns around here, and then it flows up in the ascending limb. And these two limbs, they are very close. They are lying close to each other, and they can influence the concentration of filtrate in one another. It means that this can influence the concentration of filtrate in this, and they use the small interstitial space between them. And now let's see how that is done. There are two types of countercurrent mechanisms. What does countercurrent mean? It means that there are two channels or two tubules in which the fluid is flowing in the opposite direction, and those two tubules, they are lying close by, so they can influence each other. We have a counter current multiplier, then we have a counter current exchanger. Now let's see what is our counter current multiplier. Our counter current multiplier is our loop of Henle of the juxtamedullary nephrons. Remember, juxtamedullary nephrons are the one which have long loops which dip into the medulla. So this is the descending limb of the loop of Henle, and this is the ascending limb. In the descending limb, the filtrate is coming down. In the ascending limb, the filtrate is going up. Now these two, they are lying close to each other, and because of their proximity and because of the opposite direction of the fluid in both of these tubules, this can influence the concentration of filtrate in this. There is small interstitial space between them, so this is interstitial space. So now just imagine that if this tubule this tubule, it changes the concentration in the interstitial space. So because of that changed concentration in the neighborhood of this tubule, the concentration of filtrate in this tubule will be affected as well. And then we have another mechanism which is known as counter current exchanger. What is counter current exchanger? We have vasa recta. Those vasa recta, they are coming from the efferent arteriole. Now this is what we have to understand, that in the vasa recta, adjacent to this, in this limb with over here, in this limb, the blood is flowing down, and then it turns, and over here the blood is going back. So over here it is coming down, and then this in the venous part, it is going back. So this maintains the concentration gradient which is created by this system. So this system, it creates the concentration gradient to concentrate the filtrate, and then this system, it maintains it, in a way it keeps that concentration gradient present there. Now let's see how they operate together. Like I said before in the previous slide, these two countercurrent mechanisms, they work together. Which two countercurrent mechanisms? The loop of Henle, the opposite direction of the flow of filtrate in the loop of Henle, and the opposite direction of the flow of blood in the vasa recta. Together, they maintain medullary osmotic gradient from renal cortex through renal medulla. So there is an osmotic gradient which is present from cortex to the medulla. In the cortex, the osmolality of the fluid, the osmolality is 300 milliosmoles. It is just like the filtrate and the blood, they are isotonic. And as we move towards the medulla, the osmolality at the papilla of the pyramid of the medulla, it is 1200. And there is a gradient which runs from 300 milliosmol in the cortex to 1200 milliosmol at the bottom of the medulla. And the counter current multiplier, it creates the gradient, it means the loop of Henle, and the counter current exchanger, it preserves the gradient, it means the vasa recta, because in vasa recta also the blood is moving in two tubules in the opposite direction, and then also vasa recta, they are moving in opposite direction to the loop of Henle, to the ascending and the descending limbs. And then what happens, that final job is done by the collecting ducts. Okay, so these two, they are creating the gradient in the interstitial space or in the medulla, by and large in all of the medulla. The medulla, as we move from cortex to the medulla, the salt portion, it increases, the osmolality increases. Then collecting ducts, they use that gradient to concentrate the urine. Now let's look at this diagram. It says we can see what we just talked about. So this is juxtamedullary nephron. So just look at the position of this juxtamedullary nephron. As these loop of Henle's, they are present here. It is concentrating it is creating a pressure gradient and concentrating the filtrate. And so osmolality in the cortex, it is 300 milliosmol, which is isotonic to the blood. As it moves down, the osmolality increases till at the papilla it is 1200 milliosmoles. Now let's look in this slide. The juxtamedullary nephrons, they create an osmotic gradient within the renal medulla that allows the kidneys to produce urine of varying concentration. So there are three key players. First of all, the gradient, it is created by the by the juxtamedullary nephrons, by the loop of Henle. So this, what does it do? The osmolality of the medullary interstitial fluid, it is increased. As we go down, the osmolality of the medullary interstitial fluid is increased. And then the vasa recta, they come into play. The vasa recta, they preserve that concentration gradient. And then the collecting tubule, it uses that concentration gradient to concentrate the urine. Countercurrent multiplier, it involves the nephron loop, and it depends upon three features. Those three, the first of all is that the filtrate, it is flowing in the opposite direction in the nephron loop. So in the descending limb, it is coming down, and in the ascending limb, it is going up. This is coming down and this is going up. This helps to concentrate the interstitial space in the medulla. Then the second thing is that they have different different permeabilities. We know the descending limb, it is permeable to water, whereas it is impermeable to the solute. So water can come out of this limb. Whereas the ascending limb, it is permeable to solute, and it is impermeable to water. So solute, it can come out of this limb. So these, and then there is active transport of solute out of the ascending limb. These three are the characteristics which which help in this countercurrent multiplier to make the medullary interstitial space very salty. Let me just rub this so this slide is not dirty. And now these limbs of the nephron, they are close to each other. Because they are close to each other, they can influence each other through the interstitial space between them. And the interstitial fluid in that interstitial space, the osmolality of that fluid is going to affect the other limb. Yes, we went over this figure, so it is the same thing that that the fluid flowing in the one in the ascending limb of the loop of the Henle, it changes the osmolality of the interstitial fluid, and that changed osmolality of the interstitial fluid, it influences the descending limb, and from the descending limb more water it comes out. We know that in the ascending limb it is impermeable to water, but it is permeable to solute. So the solute, it is absorbed, and then also there is active secretion of sodium from this limb. Because of that, the interstitial fluid, it becomes more salty. Its osmolality increases. Now because of this increased osmolality, the water, it comes out from the ascending limb, and as a result the concentration increases in this descending limb, and the osmolality, it increases. And then as I said before, this is used by the collecting duct to concentrate the urine. This slide, it just says the things I already said. I'll quickly go over them and then we will go to the diagram. So the ascending limb of the loop is the main character. Just consider the ascending limb of the nephron loop, the one which is going to start everything. So it is impermeable to water and selectively permeable to the solutes. Sodium and chloride are actively reabsorbed in the thick segment. Some are also passively reabsorbed. What does this mean, reabsorbed? It is mean they are going towards the blood. So let me again try to draw. This is the ascending limb. From here, the sodium and the chloride, they are coming, they are to be reabsorbed in the blood, but before they enter the capillary, they are in the interstitial space, and they are changing the osmolality of the interstitial fluid. And this interstitial fluid, I have made it over here, but it is this is where the descending limb is lying. Descending limb, it is lying in the same interstitial fluid. So the osmolality of this interstitial fluid, it is going to affect this descending limb. So this is what this says: descending limb of nephron loop is freely permeable to water and impermeable to solute. So now this increased amount of solute present in the interstitial fluid, just imagine this is here in the middle. It cannot go in the descending limb, but water can come out of the ascending limb. So water will come out of the ascending limb, and in this way the concentration of filtrate will increase here. It will increase till here, till the filtrate moves here. Again the ascending limb is going to remove the solute and make the filtrate osmolality less in the ascending limb and high in the interstitial fluid, and this process is like a positive feedback. It keeps on going on. The more NaCl the ascending limb actively transports into the interstitial fluid, the more water diffuses out of the descending limb. So it makes sense because the ascending limb, it is increasing the osmolality in the interstitial fluid. And the more water that diffuses out of the descending limb, the saltier the filtrate becomes, right? This also makes sense. Then the ascending limb then uses the salty filtrate to further raise the osmolality of the medullary interstitial fluid, because in the ascending limb active transport is happening. So the amount of solute, the descending limb, it is concentrating the filtrate, and then the ascending limb, what it is doing, it is the naughty one, what it is doing, it is taking that solute and it is shifting it to the interstitial fluid. So again the filtrate is becoming less concentrated in the ascending limb. So this there is a constant difference of 200 milliosmoles. It exists between the two limbs of the nephron loop and between the ascending limb and the interstitial fluid. And this difference is multiplied along the length of the loop from 300 to 1200 milliosmol. And we see still the difference even here is 300 milliosmol. Now let's see, I was waiting for this diagram to come so we can now understand, we can now visualize the things we spoke about. So this is the descending limb, right? In this the filtrate is coming. The osmolality of the filtrate is 300 milliosmol. It is isotonic with the blood. It comes down, and this is this thin descending limb of loop of Henle. It is impermeable to the solute, but it is permeable to the water. So the water is going in the interstitial space, and after the interstitial space it will go in the blood, right? So now just imagine the filtrate, it is moving down, and then this filtrate, for the starting I will consider that the osmolality is 300. So this comes here in the ascending limb. Ascending limb has a thin segment and a thick segment. In the thin segment there is some passive reabsorption of the sodium takes place. So sodium is reabsorbed to be shifted to the blood, but before it is shifted to the blood, it is present in the interstitial fluid. This is where the interstitial fluid is. Now moving further up, this is the thick portion of the ascending limb of the loop of Henle. This thick portion, there is active transport of the sodium, potassium and chloride. They are actively reabsorbed from this portion, and when they are reabsorbed before they go in the blood, they come in the interstitial fluid. Now the osmolality in the interstitial fluid has increased. There is more concentration of fluids in the interstitial space compared to the this descending limb. Now this descending limb is impermeable to solute, so solute cannot go inside, but water comes outside. So that is how, as the filtrate it moves down, it becomes concentrated till it reaches here. Over here the osmolality of the filtrate is 1200, and now it starts moving up. When it moves up, now this ascending limb is naughty, right? So this the descending what does it do? Because it is capable of active transport, it has energy, it has ATP. So what it does, there is some passive diffusion in the thin limb, but in the thick portion it again, it takes that solute and puts it in the interstitial fluid. So all the hard work that descending limb was doing, actually descending limb is passively doing it, this one is doing the work. So again it has taken out that solute, and which is sodium, chloride and potassium, and it is trying to reabsorb it, but before it goes into blood it comes in the interstitial space. Now again, so this maintains a concentration gradient. This is known as multiplier. So it does again and again, and the urine becomes concentrated and concentrated. So when it filtrate is leaving here, it is actually dilute. It is dilute because now the collecting duct is going to use this concentration of the medulla, this 1200 milliosmoles, to concentrate the urine. Now let's see in little more clear detail. So that was the overall picture. So that is how that positive feedback is. Now let's see. So the step number one is that filtrate. It is entering the nephron loop. It is isosmotic to the blood. So the blood osmolality is 300 milliosmoles. This filtrate is 300 milliosmoles. Now it is going down the descending limb. As it is going down the descending limb, it is permeable to water. Water is reabsorbed. It is impermeable to solute. So this is becoming concentrated. And as it moves down, it becomes concentrated. And till the water it moves out of the filtrate in the descending limb down the osmotic gradient, this concentrates the filtrate. And now what is happening? Let's see at the step number 3, the filtrate reaches its highest concentration over here in this part, the hairpin turn. They call it the hairpin turn. Over here it is 1200 milliosmoles. This is the concentration of the filtrate at this point. Now what is going to happen? Now this filtrate has started to move up in the ascending limb. And what is the ascending limb is doing? Sodium and chloride are pumped out of the filtrate. This increases the interstitial fluid osmolality, and this decreases the osmolality of the filtrate. See, when the filtrate has passed through this ascending limb, the osmolality is 100, because this ascending limb, this has active mechanism to transport sodium and chloride out of this into the interstitial fluid. And this interstitial fluid osmolality, this is the one which is causing this osmosis of water outside of this descending limb. So in this way, this ascending limb, it is influencing the concentration of filtrate in the descending limb, because they are they're close together in the tight space, and this interstitial fluid is influencing this portion as well. And now let's see what happens next. The filtrate is at the most dilute stage over here. When it has crossed over here, it is at the most dilute stage. It leaves the nephron loop at 100 milliosmoles. It is hypoosmotic to the interstitial fluid. So this is what is happening in the loop of the Henle. Now don't think that the loop of the Henle, when it is leaving, the filtrate in the loop of the Henle is 100 milliosmol. So it means the urine is dilute. No, actually what it has done, it has increased the osmolality of the interstitial fluid in the medulla. At the level of the papilla, deep inside the medulla, the osmolality is 1200 milliosmol. Now the collecting ducts are going to use that osmolality to concentrate or dilute the urine as per the need of the body. All right, now let's see what is in this slide. So now that we have counter current exchanger. Let's first discuss the vasa recta, and then we will go to the collecting duct. For now, I hope that you understand that what that loop has done. It has increased the osmolality in the medulla and the interstitial fluid in the medulla. All right, so now we have counter current exchanger, which is the vasa recta. The vasa recta, they make the counter current exchanger. Vasa recta, they are highly permeable to the water and the solutes. Now don't think that in the vasa recta, again, like I said, in the descending limb of the loop of the Henle, it is only permeable to water, and then the ascending limb is only permeable to solute. Now we are talking about the capillaries. So the capillaries, all throughout their length, they are permeable to the water and the solute. Do not mix them with the um, with the tubule. Now we are talking about capillary, and throughout their length they are permeable to both the water and the solute. And the flow of blood in the vasa recta is also counter current. It is also like hairpin turn, just like in the over there it is also hairpin turn. It means that again the fluid, it is flowing in the opposite direction. So blood can exchange sodium chloride and water with surrounding interstitial fluid as it moves through the adjacent parallel sections of the gradient. Blood inside the vasa recta, it remains isosmotic with the surrounding interstitial fluid. So this is important. What does it mean? It means that, just imagine there is a tubule lying uh, there is a tubule lying with the vasa recta. So the osmolality in the vasa recta, it is the same as the osmolality which is present in the interstitial fluid. It is isosmotic with the surrounding interstitial fluid. And vasa recta, it is able to reabsorb the water and solutes without undoing the osmotic gradient created by the countercurrent multiplier. It means as these vasa recta are going in, their osmolality is also increasing in the medulla as they're going in, because they're isotonic or isosmotic with the interstitial fluid. Now, this counter exchanger, I'm making mess. So this counter exchanger, it preserves the medullary gradient. And how does it do that? By preventing rapid removal of salt from the interstitial space and by removing the reabsorbed water. So it preserves the gradient, medullary gradient, which is made by the multiplier. Water in the ascending vasa recta comes from the descending vasa recta or is reabsorbed from nephron loop and collecting duct. As a result, the volume of blood at the end of the vasa recta is greater than at the beginning. Now let's see what is happening in the vasa recta. When we visualize, it becomes easier to imagine. So these are the vasa recta. This is the blood is flowing down, and over here the blood, it is going back up. And you see the osmolality in the vasa recta, it is same as that of the interstitial fluid. So the water which is absorbed here, this is the water which is coming from this part of the vasa recta. This is what in the previous slide the last point was, that this water when it is coming out of this portion because of the osmolality of the interstitial fluid, and this water, it is reabsorbed over here. So the volume of so it is removing the water, so the concentration, it won't be disturbed. So the volume of the water, it is more as the blood is returning to the it is returning back, and in this way it maintains the osmolality. It does not disturb the osmolality. It is working to keep the osmolality maintained in the medulla. It is trying to keep the medulla more salty compared to the cortex. I hope I have been able to explain to you somewhat what is happening. So what has happened now, that we have a very salty um, medulla. In the medulla, the osmolality near the apex or near the papilla of the pyramid is 1200 milliosmol. Now that osmolality, it will be used to concentrate or dilute the urine as the body needs. So without gradient, it would not be able to raise the urine concentration greater than 300 milliosmol to conserve the water if that gradient was not there. And the overhydration, it produces a large volume of dilute urine. Now our hormone, antidiuretic hormone and aldosterone, they come into play. When the antidiuretic hormone production is less, dilute urine with osmolality as low as 100 milliosmol, it is produced, because we know antidiuretic hormone, what does it do? It creates the aquaporins in the collecting duct, and those aquaporins, they absorb the water back in the body, and concentrated urine, it is released in the body. And when it is low, those aquaporins are not formed and the urine is going to be dilute. Now, if aldosterone is also present, it is going to reabsorb the sodium, and when that sodium is reabsorbed, water follows and it makes the urine further dilute. In case of dehydration, the opposite happens. We have lots of antidiuretic hormone which is released by the posterior pituitary, and that antidiuretic hormone, it makes aquaporins. It opens aquaporins in the collecting duct, and from there lots of water is reabsorbed back into the blood, and urine it can and the urine it can become very concentrated. It can be up to 1200 milliosmoles, and in severe dehydration almost 99% of the water is reabsorbed. Now let's see what happens when we are overhydrated. When we are overhydrated, there is decreased osmolality of the extracellular fluid. It decreases the release of ADH from the posterior pituitary. It decreases the number of aquaporins in the collecting duct, which decreases the water reabsorption from the collecting duct. As a result, we have large volume of urine, and this large volume of urine it is dilute. So in the absence of ADH, uh, this urine has not been concentrated. So because now the concentration of the final step in the concentration of the urine has to be done by the collecting duct, and we know collecting duct it acts under the influence of antidiuretic hormone, just so that you can see that where we are going. So we had this osmolality at 1200, but because the ADH is not here, the urine aquaporin has not is not present, the urine is dilute. Now let's continue with our story. What happens when we are dehydrated? Because now we want to concentrate the urine. Maybe you thought that there is some disconnect between when I said when we are overhydrated. So let's see what happens when we are dehydrated, because now this osmolality will be used by the collecting duct to remove the water from the filtrate and concentrate the urine. Now this osmolality is going to play a role. So what happens when the osmolality is increased in the extracellular fluid? It means in the blood and the extracellular fluid, and it causes the release of antidiuretic hormone from the posterior pituitary. This increases the number of aquaporin channels in the collecting duct. Now there is increased reabsorption from the collecting duct. And why is this water readily moving out? Because there is this gradient in the interstitial fluid. Medulla, it has more osmolality compared to the filtrate, so water is moving out. Then ADH, it also causes the movement of urea from the filtrate into the interstitial space, and then this urea it is reabsorbed in the proximal tubule. So this urea it also causes this osmolality gradient in the interstitial fluid and the collecting duct. So in this way the water is removed from the filtrate, and we get a very concentrated urine. The urine can be concentrated up to 1200 milliosmoles, because this is what the osmolality in the medulla is. In severe dehydration, the urine can be concentrated up to 1200 milliosmoles, and this is regulated by the antidiuretic hormone. Let's read a few points about the urea. What role is urea playing in medullary osmolality? So urea it helps in the medullary gradient. How does it help? Urea it enters the filtrate in the ascending thin limb of nephron loop by facilitated diffusion. So like I said before, in the proximal tubule the urea it is reabsorbed almost 50% of the urea. Then it enters in and then in the thin ascending limb it re-enters the filtrate, the urea. Now that urea, it goes to the collecting tubule, and when the water is reabsorbed from the collecting tubule under the influence of the ADH, now the concentration of the urea in the collecting tubule, it increases, and because of that the urea, it also moves to the interstitial fluid of the medulla, and in this way it makes the medullary gradient. Urea then moves back into the ascending thin limb, and it keeps on doing that, and in this way it maintains the osmolality in the medulla. I hope I have been able to clarify this for you. um, if there are any questions, please you can send me an email.